the human brain, the most complex and least understood organ in our entire body. It contains everything that makes you, your memories, your personality, your imagination. For over half a century, scientists have dreamed of connecting this biological supercomputer to machines, a direct bridge between neurons and digital systems. The benefits could be life-changing, restoring vision to the blind, movement to the paralyzed, even offering new senses we've never had before. Today, in the 21st century, that dream is no longer science fiction. Multiple companies are racing to create the world's first reliable brain-computer interface. At the center of attention for nearly a decade has been Elon Musk's Neuralink. But in recent years, a quieter yet significant rival has emerged, Precision Neuroscience, founded by one of Neuralink's own co-creators. And their approach to solving the BCI challenge couldn't be more different. When Neuralink was founded in 2016, its ambitions immediately captured the world's imagination. The company's central idea was bold: insert ultra-thin threads, each carrying dozens of microscopic electrodes, directly into the brain's cortex. These electrodes could both read signals from neurons and stimulate them, effectively creating a two-way communication system between human thought and digital machines. The procedure was so delicate that Neuralink even designed a surgical robot, called the R1, to handle the implantation. Each thread is thinner than a strand of hair, but it still penetrates the brain tissue by several millimeters. This level of invasiveness brings with it incredible precision, but also unavoidable risks. In fact, Neuralink's first human patient, 29-year-old quadriplegic Noland Arbaugh, initially showed amazing results, controlling a computer cursor and playing games with his thoughts. But within weeks, most of the electrodes had retracted from his brain tissue, threatening the functionality of the system. Neuralink managed a temporary software fix, but the episode raised questions about long-term reliability. The problem here is fundamental. When you pierce brain tissue, the body responds defensively. Scarring and inflammation can occur, sometimes causing the electrodes to lose contact or be rejected entirely. Neuralink insists these issues can be overcome, but critics argue the very design of the system guarantees a certain level of tissue damage. Despite these concerns, Neuralink's broader vision remains as ambitious as ever. Beyond treating disabilities, Elon Musk talks about using the technology to achieve symbiosis with artificial intelligence. In other words, merging humans and machines in a way that could enhance our capabilities, even to superhuman levels. Whether you see that as exciting or terrifying largely depends on your outlook. This is where precision neuroscience comes in, offering a fundamentally different approach. Founded in 2021 by Dr. Ben Rapoport, one of Neuralink's original co-founders and a practicing neurosurgeon, Precision prioritizes safety and practicality above all else. Instead of inserting threads directly into brain tissue, their system, known as the Layer 7 cortical interface, is designed to rest on the surface of the brain. Imagine a thin, flexible film, just 1/5 the width of a human hair, gently conforming to the brain's contours. It carries over 1,000 electrodes, capable of capturing neural signals with remarkable clarity, but without ever puncturing the tissue. This difference is critical. Because the implant sits on the surface rather than inside the brain, it causes no scarring, no damage, and carries minimal risk of rejection. It can even be removed safely, something far harder to achieve with deeply embedded threads. In some trials, Precision has managed to place multiple arrays on a single patient's brain at once, scaling the number of electrodes to record unprecedented levels of detail. While Neuralink focuses on permanent, high-bandwidth implants that could theoretically enhance humans, Precision's philosophy is much more grounded. Their implants are often designed for temporary use, up to 30 days, helping patients undergoing neurosurgery or recovering from neurological conditions. The company's leadership describes their mission simply: to improve patient outcomes and quality of life, not to merge people with AI. Of course, Neuralink and Precision are not alone in this race. Other players have introduced even less invasive methods. Synchron, for example, avoids brain surgery altogether by delivering its device through blood vessels in the brain, similar to a stent used in stroke treatment. The procedure is minimally invasive and has already shown success in human patients, though the quality of signals it can capture is lower compared to Neuralink or Precision. Meanwhile, BlackRock Neurotech, one of the oldest BCI companies, uses rigid silicon electrodes that penetrate brain tissue. Their technology enabled a paralyzed patient to speak again by decoding his attempted speech in real time. The emotional impact of that breakthrough was profound, not just for the patient, but for the entire field. Together, these approaches show that the BCI industry is diverse, experimental, and rapidly evolving. Each method carries trade-offs: invasiveness versus safety, signal quality versus surgical risk, permanence versus flexibility. What makes the contrast between Neuralink and Precision so fascinating is that they represent two very different philosophies for the future of brain-machine interfaces. Neuralink sees the brain as territory to be conquered with deep, penetrating threads and a futuristic vision of human-AI symbiosis. The risks of tissue damage are accepted as part of the price for ultra-high bandwidth connections. Precision neuroscience, on the other hand, prioritizes safety, reversibility, and medical utility. Their system avoids damaging the brain at all, aiming to provide immediate clinical benefits rather than speculative future enhancements. It's the difference between aiming for a moonshot and building a safer, more incremental bridge. Both paths could lead to breakthroughs, but the risks and ethical implications diverge sharply. All of this leads to a deeper, more uncomfortable question: should we be doing this at all? When it comes to medical applications, helping paralyzed patients regain mobility, restoring speech, or giving sight to the blind, the answer seems obvious. Few would argue against using BCIs to treat disease and disability. But what about beyond that? If brain implants could enhance memory, intelligence, or even enable new senses, who gets access? And what happens if society divides between the enhanced and the unenhanced? There are also pressing legal and ethical issues. Who owns the data generated by your brain? How should it be stored, and what protections are in place to prevent abuse? Regulators like the FDA insist these concerns are built into the system, but the stakes couldn't be higher. In a world where even smartphones leak sensitive data, the idea of hacked brain implants feels like something straight out of dystopian fiction. The race to develop brain-computer interfaces is more than a technological competition. It's a philosophical one. On one side, Neuralink pushes toward a radical future where humans and AI merge. On the other, Precision Neuroscience offers a cautious, patient-centered alternative, prioritizing safety and practicality. Both approaches have their merits, and both carry risks. But together they force us to confront the ultimate question: not just what's possible, but what's worth doing. Because in the end, brain-computer interfaces aren't just about technology. They're about what it means to be human, and how much of that humanity we're willing to modify in pursuit of progress.